Okay, so I think we are a couple minutes ahead of schedule. That is great. Hi, my name is Ming. I'm currently an assistant professor at Mayo Clinic. Our next session is our keynote speaker, Urbanek. It is my distinct honor and privilege to introduce him to our symposium today. Dr. Urbanek is an integral member of the R Core development team, and please join me in welcoming him. Dr. Urbanek currently serves as the senior lecturer of data science in the Department of Statistics at the University of Auckland in New Zealand. Dr. Urbanek has developed a remarkable career spanning continents and domains. Before his tenure in Auckland, Dr. Urbanek dedicated 15 years as a researcher at AT&T Research Labs. He has also served as an assistant researcher at the Department of Computer-Oriented Statistics and Data Analysis at the University of Augsburg, Germany, where he obtained his PhD in statistics. Beyond his academic pursuits as a key member within the R core team, Dr. Urbanek maintains R for Mac OS, produces binaries and packages, and makes R accessible and powerful for countless users around the globe. Notably, his work on the collaborative R environment, R Cloud, has made statistical analysis more accessible and interactive than ever before. Now, without further ado, let us welcome Dr. Urbanek to the stage. Thank you. And please feel free to type your questions in the chat box as we go along. We will have 10 minutes at the end for Q&A.
Simon, you are muted.
I think you are muted.
Hopefully. So Sanju, thank you very much. I'm really appreciate being able to be here and talk to you about some R-related things. When David asked me, he was talking about, what can we talk about that people don't already know about, or what can be interesting, because this is a symposium on statistical computing, but I'm sure a lot of you are already very familiar with many different aspects, and R is sort of well known for being a system for statistical computing. So which parts could be interesting that maybe are not as well known? So I figured two aspects that are quite interesting, but R doesn't necessarily get credit for, are handling of large data sets and using R as a service. So these two aspects, I think, I want to talk about a little more. So let me first show roughly the overview of what I'm planning today. So I just want to very quickly talk about R. Obviously, a lot of you are already familiar with R. And then the two aspects. One of them is how can we apply R to large data sets? What are the pitfalls? What are the different methods we can use? And actually trying to argue that this is not really a bad idea. When I was at AT&T, we've been using R to handle data sets in many hundreds of terabytes of size. So R can do it, but you have to be a little smart about how we do it. And the second question is how can we use R as a service, which means we have all this really cool technology. We have so many different models and other things that we, of course, can leverage, but how do we make it so that others can leverage this information as well? So it's not just us statisticians being able to use the information, but others as well. So using R as a service is something that's quite doable, and I think it's a very valuable feature of R that this is a little more about that. So first, obviously R project for statistical computing is the full official name. As it already stands in the name, this is quite pertinent to our symposium on statistical computing. So it is the de facto language for statistical computing. Many of the methods that are current are implemented in R. It's a domain-specific language. This really has been designed to allow us to analyze data sets. It's not a general purpose, which is some people think, but it's actually highly efficient for the things that we do, which is analyzing data, transforming data. It's also really good at visualization. We have a lot of visualization methods, plots, be it static ones or even interactive these days, with support for web plots. And it is actually highly efficient at vector and matrix multiplications, which is something we want to do. The language is also designed so that it's really easy to express things, such as, if you want to do some kind of data transformation, you really just write it out the way you would in math, which is something that we take for granted, but actually most languages don't allow you to do that. And this is part of the reason why we like it so much. And finally, it's highly extensible. That means people can just add their own software, their own methods, which is why we have such a large library of statistical methods, which have me as was saying, as being part of our journal editorial board. So we see all the articles that are coming whenever people come up with new methods that typically follow up with having an R package that allows other people to use that method, which is great, and that's what we use R. So I think we're all familiar with R and its benefits. So what about dealing with large data sets? So R itself is most efficient when it can work with all the data in memory. So that means the operations just are as fast as possible because, as I was saying, we can easily use metrics and vector operations. So the first hurdle, and this is where perhaps R gets the reputation of not being the most efficient in this respect, is we need to read the data into R. And if you try to do this using the standard methods, well, it may not be what you think. So for example, I'm using just a simple example here. It's the New York City taxi data sets, just 1 month of the data. There are 18 variables. The whole size of the data set is approximately 2.6 gigabytes. So, relative to, let's say, the sizes of computers, computer memory it isn't great. It's pretty decent, but it's not huge. There are about 50 million rows. Well, if you just naively say read.csv in R, it will take you more than 3 minutes. So that is, of course, not great because you wonder if anything's happening at all, if it will finish at all. Well, first thing people would usually tell you is, well, you can always subset. So you can either subset rows or columns. Columns if you're just interested in certain information, or rows if you're just trying to look at some subset of the data set. And obviously that's possible, but that's not a great solution because you may be interested in outliers or other features that you cannot just simply get out of the data set. So in fact, there are tools and packages in R where you can do it much more efficiently. So for example, IO Tools is one such package that its purpose is just to make sure that we can do input and output operations as efficiently as possible. So for example, there is a read CSV version of it as well. And as you can see, suddenly we're back to 25 seconds. Now that's still not negligible, but it's pretty much as good as you can do with just single CPU. So what's the next step? Well, we can use thread multi-threading. So that means use multiple cores of a CPU at the same time. One package that can do that is Arrow. And here now, if you look at here, what I'm showing, this is the time that the CPU has to spend, but this is the actual time on the clock. So essentially how long it takes, and this tells you that this is heavily parallelizable, which means all these cores together take the same amount of time roughly what we saw before, because there is in fact the amount of work that's necessary, but we can do it in 5 seconds. So this week is getting to sizes where it is quite conceivable. Now, anyone who has dealt with big data sets will tell you actually something else, which is you just shouldn't be using CSVs to start. So in fact, if you just change the format, in this case, if I just change the data set to use the K format, which is what is mostly used in clusters to store data, then you will see that not only are we getting down to 1.5 seconds or more than 100 times faster than what you've seen before, but also actually the data size goes down because these formats are polymer-oriented formats and they can be easily compressed. So we're quite a few benefits here. So what about processing? So we get the data sets into R. So, in fact, as I was saying, R is pretty good at handling the large data sets as far as manipulations of the variables or running models and so on. So here are just a couple of examples just to give you a rough idea. So this is just saying we have our 15 data sets. If we do things like sort, which is not trivial, obviously has to have access to all the data. So here I'm just looking for outliers. There's some really strange numbers and quite often repeated for some reason. So it'll be interesting to look into that. So it takes only 300 milliseconds to do that. Simple computations, again, really, really fast. No problem here. Just checking out left some really ridiculous longitudes since this is supposed to be New York City. So we can just look at these things. Other operations such as looking at values. So here again, they're just looking at the fact that, yeah, there are different codings of the same variable, probably mistakes, we probably fix them. All super fast, everything you can do, like using it as an exploratory data analysis. Within less than a second, you can do all these operations. Or even you can just fit models. Again, takes only a few seconds, works reasonably well. So what I'm trying to say here is that, once you've got the data in, usually R is pretty good at being able to handle data sets of, a couple dozen millions of rows. So it is feasible. There are a couple of hints on what you can do. For example, graphics work, but you have to be careful. If you were to draw, millions of data points with fancy symbols, that would probably take quite a long time. Especially with base graphics, it's really fast. So that means, for example, using the dot makes the graphic work even with millions of data points. Maybe another thing that people may not be aware, there are these special commands, device, hold, and flush, that allow you to essentially tell R, hold on, I don't need to see everything all the time. I will just create the plot and then just look at the result. That allows me to sort of hold the device so it doesn't try to redraw everything on every few seconds. As I was saying, you want to use matrices for numeric data because this is the most efficient operation we have. And they are optimized function. They are, in fact, even parallelized on multi-core CPUs, such as call sums, co-rows, lengths, and so on, instead of using, the equivalent apply and functions. And the last point I wanted to make is that, try to use the latest version of R, because there's a lot of development in R, even though R has been optimized for the longest for us, the internal code concerns, but also new features have been added, such as alternative representations. So I won't go into that. That's another aspect where there are packages that allow you to not just load the data directly all in memory, but allow you just to have a sort of a proxy, and then they can represent things internally and fetch things as they go. But this is also used for other use cases, such as if you have sequences, they are not actually truly stored in memory, it's just the information about the sequence that's stored. There is a byte compiler that tries to compile code so that it's more efficient, and it pretty much happens automatically. So if you use a function more than once, it actually automatically gets compiled the second time around it's being used, so that it will be even faster the next time. R tries to do pre-allocation, so if you're trying to group vectors, all the example that we were trying to avoid and telling students not to do, like appending a vector by one element at a time, is actually even more efficient these days because R tries to be smart about it. So there's a lot of things, a lot of development, and it's always good to be at the latest version of R. So what about big? And I mean, like, really big. So what we talk about now is essentially how can we use something that fits into memory that we can use on our computer. So what are the sizes we're talking about? So laptops today, it's just The current ones is between 16 32 gigabytes of RAM. Computing servers can have up to 1 terabyte of RAM these days quite easily without stretching your budget too much. And also, of course, today we have cloud computing, which means you can just buy time on arbitrary big VMs that go into really tens of terabytes if you really want to. So memory may or may not be a problem. So it depends. It's needed both for the data as well as the processing. So that means the fact that just it's enough data to load the data set doesn't necessarily mean it's enough to actually work on it. But this is sort of roughly the size we're talking about. So we typically say at least 10-to-1 ratio. So let's say with the laptops we're talking about between 2 to 3 gigabytes of data that we can use easily. With the servers, it gets one order of magnitude larger than that. Now, the fact that you can load in memory doesn't necessarily mean it's sufficient because the CPU speeds are limited. CPU sort of per core speed has not really increased dramatically in the last few years, despite that development being the case before. But what has increased is number of cores that are available. So that means parallelization may be a way to go. Now, I won't cover parallelization in depth here. I just want to mention a few things you can do, such as there are implicit parallelization, so a lot of packages, as you saw, for example, with Arrow, automatically parallelize if they find out that you have more cores on your CPU and can just simply use them. R does that to a degree as well. There are some functions that are parallelized. So that's implicit parallelization. Sometimes maybe you may need to write your algorithm in such a way that you can parallelize it because it may not be trivial. If you can, then you can use the biggest help is the package parallel as a thing. And so the easiest way is just to use multi-core, so MC lapply, multi-core lapply, for example, where it allows you just to simply spread your work across multiple CPUs cores. You can also use clusters, so the make cluster, which gets a little harder because then you have to explicitly say every command or every evaluation that you want to make, that you can send it that way. There are some good compromises. So, for example, the for each package has a do MC backend, which allows you to leverage one of these backends, such as multi-core or even Snow to do the parallelization. So there are some choices you have there. Again, I won't go into too many details here, but if your problem is speed, it's usually thinking about first, can I optimize the code? The second, can I parallelize the code? And it depends on your requirements. It's the easiest way to do that. Now, what if it's not about speed alone, but actually the data's too big? So that's typically a bigger problem because the fact if you can parallelize, meaning you can get another let's say 1 order of magnitude out of the speed, and typically that means you have to get really much smarter about how you do things. Let's say using a different algorithm, but most of the time it's at least doable. The problem is once your data does not fit into memory, there's nothing you can do because that means you cannot do the operations you did so far. So what are the alternatives? So there are pretty much two different approaches that are related but slightly different. One is that sort of is more similar to what we used to do way back, is just we read the data piece by piece. So that means instead of reading the entire data set into memory, we just start reading little piece at a time, then do whatever processing we need to do and continue working on it. The second one is we just split data into pieces and just process these pieces independently. So as you can imagine, the first one is sort of easier to do in that we can keep information around. So for every new piece of data, we can simply update our information. So it's somewhat easier to do that, as opposed to the second one, which means all our pieces are completely independent. So we have to somehow think about modifying our algorithms so that they work on pieces that are independent and then bringing the information back together that we actually want to compute, because not always is it possible to simply get the right answer directly. So first one I would call streaming or chunk-wise processing. And the second one is some algorithms that work this way, is map and reduce, or for example, Spark uses this approach. And so these are two different things that we can. Now, as we mentioned before, R is actually really good at matrix vector operations. So piecewise is actually much more efficient than row-wise. So you can think of it that, let's say, databases work row-wise, where you just have one row at a time and you do things to it. It's really much better to just work column-wise, but that means you don't want just one row at a time, but you want to have entire pieces. So that's why this whole idea of chunking, sort of working at sort of mini data sets at a time, as you can think of it, is really the best way to use R. So classic algorithms, how they are implemented. So let's say the classic MapReduce, where you just have one key value pair, which really means just one row at a time, is not a really good idea to go. So we really want to do it sort of one chunk at a time as opposed to do that. So here is one example how this can be done in R using chunk-wide processing. So there, again, I mentioned the package IO tools. There's also a package called BigLN that allows us to fit linear models using this approach where we load part of a data set and then just use update to update the model based on the next data that's being read. So we can simply start our chunk reader, we can give it a data set. It can actually be also connection, so it can be more complicated than that. And then we have the ability to just read one chunk at a time. Now, the point of a chunk reader is that it limits the size of how much data will be read at any given point, so that we can define it to be sort of the sweet spot between, we don't want two little rows because then it's going to be inefficient because we will have many, many chunks. And we don't want it too big because then we start worrying about running out of memory or it being just getting too slow. So the chunk reader allows us to define the chunk sizes regardless of how many variables or rows this are. It's really limiting by the size that will be used. So once we read our chunk, we just turn it into again our data frame, and then with the data frame we can just use our regular functions such as BigLN, just specify the formula and the data, and then we're just running a loop pretty much that just says, okay, read the next chunk, and then we just update on estimates. So you can imagine a whole set of algorithms works this way. Now, obviously, not everything can be done this way, and you wouldn't necessarily use this for, let's say, exploratory data analysis. You can actually, because if you put a plot command here, it would just update your plot every time you see a new chunk, so you can actually see how whether the properties of your data set do change over time. But normally, this is mostly intended for algorithms. This works for any data sizes. That's the beauty of it. So really, you absolutely not limit it. It's just a matter of time. So if you have a really large data set, it will just take more time to process. The memory usage is limited by definition because we're just saying we will handle as much as we can. And the processing is sequential. So that means we really need to wait for the previous chunk in order to compute the next one. The reason is because we want to update, let's say in this case, the model parameters. So if you were to need actually multiple iterations through the data set, that means you would have to restart and go back and do this again. So obviously it's ideal only for for methods that need only a few iterations, but it's not really good for anything that would need a lot of passes. This piece can now, if we relax the condition that we need the result from the previous iteration, then we can actually parallelize this. So that means we could read multiple chunks at once and just simply evaluate this code for each one of them. There is a function in this case called chunk apply. It's essentially the equivalent of apply, but instead of applying over elements, it applies over chunks. So that means it just runs the function on each one chunk at a time and does have the parallel option. So this is sort of getting us more towards the second approach that I was talking about, which was to split the data and then run things independently. Now, still here we do have a bottleneck because we're just reading the data set one chunk at a time. So even if the processing takes longer, it's fine, because that means we can be reading while we are already processing chunks in parallel. But it also limits the number of algorithms we can use, because now with the parallelized version, we can no longer reuse information we had. So for example, we couldn't do this in parallel because the update depends on the previous value of M. So we can bring that actually even further. So in real life, as I was saying, reading from a single file or data source is a bottleneck, because that means whether it's the actual reading or it's the parsing, as we've seen in the first part, that takes time. So it is a bottleneck. In reality, in fact, most places where you go that will have large data sets actually have them stored in distributed file systems, because they're just too big to store on a single hard drive. And also, it's much more efficient that way. So they actually already split, typically across many machines that just hold pieces of the data, such as using HDFS. So in that case, the nice thing is we don't have to have this bottleneck, but instead we can just simply send the data to, the code, so the computing to the data. So that means we're going to this approach where everything is done independently, and then we simply send our code to each chunk of the data to do the processing there. And that can be done on large clusters that can have multiple cores. So that means you can have multiple processes running on the same machine and many machines. And one of the example of this is Hadoop MapReduce. Now it's sort of just continuing from the thread that what we talk about doing chunkwise. Now we're just doing independent. And again, the key is, how do we make it look easy for our users? So here is what something like this would look like. Let me start here in the middle first. So here is the actual work. Oops. So this is the actual map function, which you can think of. This is the first step that gets run across every single chunk. Now, the nice thing about this is that our input is already a data frame. So we don't have to worry about any conversion thinking, and we don't have to worry about working on row at a time. Actually, we do get sort of mini data sets. So the nice thing about that is you can just simply develop your code as if you were working on a data frame in R. So there's nothing new here. You don't need to worry about anything special. You just simply write the code. You would have written it. The only thing you have to think about is that your output should be such that if I have this output from every single piece of the data, then I have to have a way how I can combine all this information to get what I actually. So in this case, I'm just doing a simple procedure here where I'm looking up the zip files from. So I do have the polygons of zip files, and then I'm just doing a point polygon test here that looks, which of the zip files contain this latitude and longitude. This is all vectorized. We're in R, so this works one data frame at a time, and then we're just getting the actual value of the zip code by simply subsetting with this sort of point polygon test. So that gives us the zip code for each of the data points, and then we just get a table that gives us the counts for each zip code in the data. So this is all fine. This is what we have done if we do this on the full data set. Now, because we're running this on pieces, we just have to summarize this information, because in each piece we will have, we could have the same zip code. So let's say the first piece has a certain number of elements in one zip code, and the second piece has them as well. So we just have to add them up at the end. Simply, we can do that by just using row names and just applying the sum over this. So this is simply making sure that our individual tables get combined into one big table at the end. And I won't go into details that there are things like we can actually parallelize this step as well, because you can just group the zip code so that as long as the same zip codes show up on the same machine in the same reducer, then we can do it as well. But the main point that I'm trying to make here is really that this code is really just exactly regular R code that we would use if we were to analyze the data set. We just have to add extra logic to combine the results. And pieces up here essentially saying where does the data set live in HDFS. And this function is just sort of a way, how do we convert the on-disk format into the data frame? So here it's just defined that we have two variables, longitude and latitude, and the separators, comma. You could have just used read as CSV here instead, but this is more efficient if you know exactly the format of your data. It's actually more efficient to use it this way and also safer. One extra thing is that unlike the chunk-wise approach where you actually have to specify what do you want to use inside these functions, because they get sent to the cluster and the Hadoop jobs is actually created and run. So here I'm saying I do need the shape variable, which actually contains the shape, the polygons and the zip codes, and that gets automatically distributed to the cluster. So the nice thing, we can use arbitrary complex R code, so any and all functionality that we already have in R can be used here. Function just take a data frame, and it's highly scalable because it just gets distributed across the cluster, and it just works that way. You don't need to worry about all these details. As I was saying, one drawback is each chunk is seen only once. So if you wanted to iterative algorithms, you would need multiple runs. There are some other approaches if what you saw is not enough. So for example, Apache Spark is, again, another layer on top of Hadoop cluster, or actually other implementation like Databricks, that allow you to define operations that are then automatically performed across the cluster. They are sort of abstract data operations, so you cannot use R code directly. Essentially what happens is that the R code you write gets sort of translated into the platform's operations, and the result gets executed. There are two bindings, the Spark R, which is the official one from Apache Spark, and then Spark VR from Studio, which uses more of the sort of the deploy verbs and translates them to Spark operations. The Spark native operations are really efficient because that's what the platform is good at, because it's written in Java and that's this on the cluster directly. But it's limited because you're just limited to the functionality that Spark has itself. So you cannot use just easily arbitrary R code. There is a way to run R code on in Spark, but it's not very efficient because it has to do because it's sort of not designed to do it this way. So it has to convert the data, send it to R, do the execution, go back. So it's actually less efficient than that. Now, alternative to Spark. So the good thing about Spark is you can do iterations because the workers are just persisting, and you can just send you send next operations to them, and that simply gets executed. So iterations are fine, as the data already resides on the workers, and you just continue working with the same data. Another one is that I'm mentioning just for completeness is Apache Hive, because it's a good way to get data out of distributed data sets, because very often you can simply define a Hive schema on a data set, and then you can use SQL operations to extract data, to transform data, so for sort of basic operations, and it just happens automatically, so you don't have to worry about it. It's a really good source for pre-processing, because you can just run Hive queries and then use them as source for either chunking or MapReduce that we saw before. So this is roughly the, so that was the part where I wanted to show how can you use R really efficiently from, a single session up to cluster computing. And since we don't have too much time, I'll just carry on to go into the second part, which was how can we use R as a service. So in some sense, it's sort of similar that a lot of times all your computing on even large data set will be happening remotely. So your computers are remote, so you need to have some kind of communication. The other motivation is that we can now provide the work that we did. Let's say we created models and we want other people to use those models, do predictions, and so on. And it's normally it's fine. We can do it on our computer, but how do we take this and actually give it to other people so that they can use it in systems, they can use it in web pages. Also, that applies to data processing, to visualization. So that means we can provide visualization services, dashboards, all the way to collaborative data analytics. And we can use R as the backend for this. So here's just a simple example. How can we define an API where someone can simply do an HTTP request and just get a prediction? So here I have a GAN model that has been fitted. So I just need the model itself. And then all I need to do is just write an R function that simply takes some parameters. In this case, this will be the sort of input to the model. In this case, I'm even doing a little bit of pre-processing, so the model is actually not applied directly on those parameters. But in fact, in this case, this model is predicting the electricity load in the grid. And we're doing this by saying, okay, give me the timestamp, the outside temperature, because actually our prediction depends on are people using heating, or maybe air conditioning and so on, and also solar radiation. And we can just predict then what the load would be. So we're really just using a predict function on our model plus some processing. And that's really it. All we do is we just wrap it in as a list so that we have an output. And now if you just do a request that just says, this is power, that's the name of the function, and just set the parameters, it just returns back the prediction. And it's really, really fast. So this is using R as the backend. And you can see we're talking about 50 milliseconds for total time. And I'm actually using just the time for the request, but the total time will only to run the entire command. But that's it's really, really fast. And it's easy because all we need is just to write an R function. So something we already know how to do. But the other nice thing is that it's not limited to just regular data output. You can also use graphics. So in this case, I'm just creating, it's the same prediction, except I'm now just running a 10-minute prediction interval from the day that's being specified here. And I can just create a plot, do some plotting, and just output the plot. And if you do that, this is what will happen. So if you send a request, what gets back, you just get a PNG back with the entire prediction and error bands as we just defined it here. So R is really it's really easy to just turn your code into services that others can use. One of the nice things is that the platform can actually take care of all the details, such as if I have an error here, for example, I just said oops here, the timestamp, it just gives you a description of the error that's really just wrapping off the error object that you get in R. The same thing, if a parameter is missing, you will actually get a meaningful error here as well. And finally, you're not limited to just using query parameters in our requests. For example, if you use JSON as the body and a post request, which is sort of more common for automated REST APIs, that then actually works without you having to modify your code. It just works. These values get turned into your function parameters and the functions. So what options do we have here for the REST API? So nice thing is we can just reuse regular R functions. A lot of the complexities can be hidden, as we've seen here. So there are 3 different main interfaces or main implementations here. R actually has a built-in web server, in case you've probably seen it, everyone, because whenever you fire up help in R, it starts this built-in server, and that's many years ago, that's what it was written for, so that you can have sort of nice web pages, the text format we used to have before that. There's also package HTTP-UV. And I should mention that, obviously the built-in server is kind of complicated to talk to, but there is a nice interface to it, which is called Rook by Jeff Horner, and then that allows you to just define the endpoints. HTTP-UV is another package from RStudio that allows you to do the same thing. It's very similar. And finally, there's RServe, which has several high-level interfaces such as FastRWeb, which just allows you to define R scripts that act as the endpoints, or as REST RServe allows you to just define functions as the endpoints. So how do these things stack up as far as scalability goes? So if we were to use just regular R, we know that just starting R and running some R.
We are about to wrap up. Can you please try to get through the rest of the slides in 2-3 minutes?
Yes, that's right. So startup and loading is really slow. So how can we use it with this interfaces? So the nice thing is R can be preloaded with data and packages. So that means we don't have to worry about that. The individual request time. So one thing we have to be careful of is that whatever we're computing, really there's nothing with that amount of time will be needed to do our requests. There are other overheads such as our language overheads or interface overheads that we have to be aware of. For example, sort of one surprising thing was, let's say if you use divers, we know it's not incredibly efficient, but if you have large enough data sets, it does not. The overhead is not big enough to matter. However, if you're doing sort of quick requests on data, then it actually starts to matter, because things like the lazy loading really increase the overhead there. And of course, the other question is, well, what does it mean scalability? Can we do parallel connections, and can we do parallel R processing? So the internal server and HTTP really allow parallel connections, but the R code is always evaluated only in one session. So that means there is no parallelization in R, which is great for fast requests, but doesn't really work as well for really long time computations, because that will block everyone else while the computation is running. RServe sort of goes the other way around, where each connection is a parallel R process, so it really scales with the number of users or number of connections, and it uses shared memory, but that means there is an overhead with each new connection to the server, because it essentially just has this a quick overhead where it forks the same R process and runs in it. One thing I probably won't have time into, so beyond just regular REST APIs, we can go even further to full interfaces, such as graphical user interfaces, and that's where we want to use WebSockets that allow you to have a direct connection to your R session and talk to it continuously. Nice thing is all this can be really easily deployed. We do have Docker images, such as Docker project. And there are considerations about security that we thought about, and there are some solutions here. So finally, before I conclude, I just want to talk about some future work that we're working on. So for the large data sets, most of it is covered in package space. One work that we're working for the next version of R is actually to take the capabilities we have in RServe that, for example, R code and put them back into R itself, so that we can define graphical user interfaces with R alone without any additional help. So, and the idea is that we can have an interactive help system, so that you can actually interact with your session with the help system. We want to embed R into frameworks such as React.js.
Sorry, Simon. We do need to wrap up, unfortunately.
Yes, I'm wrapping up. And then we can have more flexible web server backends. So, for example, you can define what are required parameters and so on. So this is the conclusion. So we've been, talking about how to perform operations in R on large data sets, the different options we have, and also I talked about how can we expose R as a service using REST APIs, which extends also to things such as desktops, visualizations, and frameworks such as R Cloud. And all this is very much in active development, so we hope to sort of make it even easier for users to use this. So thank you very much for your attention.
Okay, thank you very much for the excellent talk by our keynote speaker, Simon. And I really enjoyed the part introducing Hadoop and Apache Spark. If you have any questions, please try to type in the chat box. Unfortunately, we do not have time for Q&A. And I think questions from David actually have been answered by the last couple of slides. So without further ado, let me pass the baton on to Sam and to our next session.